Hello everyone, we're going to continue talking about ocean movement with Unit 6. So our next topic is tides, and tides is the change in water level along the shoreline. And that's caused by a gravitational attraction between the moon and the ocean. Literally, the moon pulls on the ocean water and creates kind of a bulge, if you will, around the Earth. And then the solid part of the Earth moves underneath the water just slightly. And so as the water approaches land, it kind of pulls the water up onto land, and then as it moves past water, then of course the water goes back into its regular spot. And so we call that movement coming up onto shore and going back out into the ocean tides. And there are two kinds of tides. There's a high tide, which is where the water comes up very high onto the shore. And then there's a low tide, and that's where the water goes back to the ocean and leaves a lot of the land exposed. Twice a month you'll get some unusual tides. One is called a spring tide. It's an exceptionally high tide, and that is when the sun lines up directly with the Earth and the moon, and all their gravitational pulls are added up together. And so that pulls the water extra high up onto the shore, versus a neap tide, which is an exceptionally low tide, and that's when the sun is at a right angle to the Earth and the moon. And that also occurs twice a month, and that's at halfway between the full moons and the new moons. So if you take a look at these diagrams, to the left shows you the difference between high tide and low tide. Notice that the moon is there, and it's literally pulling somewhat the water away from the solid part of the Earth. Now, it happens also on the opposite side of the Earth due to the sun also pulls as well, and so you get high tides and you get low tides mostly at the north and south poles or southern poles. If you look at the diagram on the right, you will see the spring tides and the neap tides. Notice that in the spring tides, it's either the sun, moon, and Earth, or the sun, Earth, and moon, depending upon where the moon is in its circulation around the Earth. And then when it's at the first quarter and third quarter is when you would get the neap tide. Notice it makes a right angle, either sun, Earth, and first quarter moon, or sun, Earth, and third quarter moon. That's a complete right angle. And so their gravitational pulls kind of work against each other to create a low tide. And so movement of ocean is, of course, beneficial to the Earth. It keeps the temperature around the world relatively even, if you will. We don't have really, really hot spots, and even though I know we have the tropics and we have Arctic and that kind of thing, but I'm talking about extremes where life could not live. It keeps it relatively the same around the Earth, and it also keeps the water clean. And so movement of water also causes erosion of land. You know that whenever water has movement to it, it has energy to it, and when it has energy to it, it's going to take away sediment with it. It's going to carry things with it, and sediment is typically what it carries. And so the more energy that water has, the more it's going to pick up sediment like sand and debris and rocks and carry them away. And that is a removal of land over time. But as that water loses its energy and it slows down, then it's going to drop its sediment like sand and rocks and debris, and it's going to create land in a different spot. So even though you have erosion in some parts, in other parts you'll actually have deposition of land rather than erosion of land. And so this diagram shows you some of the formations that erosion and deposition can make. Notice the lagoon. The lagoon is actually an erosional figure, but the barrier island is a deposition because everything that was eroded from the lagoon got carried out into the water and then deposited. Same way with spits. As the erosion took away, you get these little formations, and sometimes currents will drop sediments and create these little pointed areas called spits. And then same with a tide island or a tombolo. A tide island would just be, let's say there was an island out in the bay, and then more sediments got dropped and created a tombolo, which connected that island to the mainland, and that's called a tide island. And then I don't think your book talks about the cuspate foreland, so I'm not even going to address it.
This film is about a frontier. You won't find it marked as a red line on a map, yet it's 5,000 kilometers long and runs around the edge of Britain. It's the coastline. This frontier that looks so permanent is in fact constantly changing in detail. The coastline is a battleground between land, sea, and human activity.
We often get the wrong impression of the coast as an environment, probably because we normally go to it on holiday when it's nice and warm and sunny and relaxing. But the truth is often more like today. It's 2 degrees Celsius, we've got a force 6 wind coming from the southwest, and masses of wave energy directed at the frontier between land and sea. The power of the waves depends largely on the distance they have to travel, and that distance is called the fetch. And there's nothing between this stretch of the south coast and Brazil, 10,000 kilometers way out there. So, what with the huge fetch from the southwest and the powerful southwesterly winds, today these two forces are working together to hit the coast really hard. I think I'd rather be on the beach of Brazil, wouldn't you?
The enormous amount of open water between America and the British Isles enables the waves to gain great power during their long fetch from the southwest. What's more, the most common wind is from the same direction, adding even greater power to the waves. One of the places that gets the full force of all of this is where this program was made, the coast of southern England, in Dorset and Hampshire. Thanks mostly to the high wave energy, this stretch of coast has some of the grandest scenery in the country. And the shapes of the landforms are thanks to a lucky mixture of rocks, some hard, some soft.
And it couldn't be clearer. Hard rock, just a few meters away from soft rock.
The harder rock is on the outside, facing the sea. It's called Portland stone. This works like armor, protecting the softer rocks behind from the waves. But the sea is a very powerful force and always finds a way through. It seeks out weaknesses in the outer wall and drives holes through.
Once it's punched through the Portland stone, the water eats away at the softer rock behind, creating coves and inlets.
This erosion that's happened in the softer rock behind the hard outside wall is something that's going on all along this piece of coast. In one spot, the sea has taken the process much farther and created one of South England's great beauty spots, Lulworth Cove. We can speed things up to show how the cove was formed. First, we need to whiz the clock back a few thousand years. Right. So hard rock on the outer wall, soft next behind it, then hard again behind that. Then, the start of the process is the sea punching a hole through a weakness in the outer wall. Once into the soft rock, the sea starts to erode sideways, and things speed up considerably until it reaches a barrier, the second wall of hard rock. Result, the shape of Lulworth Cove today. Recently, geologists have been able to apply this process at Lulworth to other parts of the south coast. They now have a much clearer picture of how large stretches of coast have evolved over thousands of years. David Harlow, Bournemouth Borough Council.
Has the coastline always been this shape?
No, not at all. This is the coastline we recognise today, from Old Harry Rocks all the way around Poole Bay to Hengistbury Head, around Christchurch Bay to Hurst Spit and to the Needles. But 9,000 years ago there would have been a continuous chalk bridge from the Needles to Old Harry Rocks. By about 6000 BC there must have been a large erosion bay forming, a much larger version of the Lulworth Cove that you can see now. Probably by 2000 BC there was a very much bigger bay, and by Roman times the coast was beginning to look as it does now, with two distinct bays.
Much of the time, changes to the coastline, like those described by David Harlow, happen so gradually that the process is hardly noticeable. You could sit around for months without spotting a single change.
But it can be extremely quick. The crew of the Eastbourne lifeboat saw something huge happen with their own eyes on this stretch of coast at Beachy Head. The coxswain of the lifeboat is David Cork. Could you tell us what happened here, David?
Well, we were on our Sunday morning exercise coming round Beachy Head, and we saw the contour of the shoreline has changed considerably by this massive rockfall.
100,000 tons of white chalk had fallen from the cliff into the sea, joining the lighthouse to the mainland.
So you're not going to take us in to have a look then?
Absolutely not. This is as close as you're going to get. The cliff face is very, very unstable at this present time. It'd be far too dangerous for anybody to get on the shoreline.
The closest anybody can get to the rockfall is up here, about 150 metres above it. And absolutely typical of the coastal frontier is that it was really two forces which caused the fall. Firstly, high wave energy smashing at the cliffs during a storm, and secondly, 2 weeks of heavy rainfall working its way into the chalk and loosening and weakening the rock. The result, a mass of material fell away from the cliff face below me. So, even during the short period of time we've been making this programme, the frontier between land and sea has moved. And to be honest, nobody knows when it'll move again, so I'm off.
The 100,000 tons of rock that fell off Beachy Head are only a fraction of the millions of tons of coastline that are eroded every year. But where does all this material go? What on earth does the sea do with it?
On a chunk of coastline like this, with such huge features, it's easy to forget the little things, which are just as important. And here they are. Rivers carry material with them, so do glaciers, and so does the sea. And the sea's material is called beach sediment. A lot of this will have been brought along the coast from the southwest, which is the main direction of wave attack. It's either been removed from the cliffs by erosion or brought down to the shore by rivers. Some of this might actually have come quite a long way. Like, for instance, this reddy brown stuff looks like a sandstone from the Devon coast, 50 kilometres back there.
What's happening to the beach sediment at the water's edge looks a bit haphazard, but in fact there's a very regular movement going on here. How the beach sediment moves you can see by concentrating on one single pebble. A wave rolls up the beach diagonally from the southwest and takes the pebble with it, the southwest being the direction of the fetch and wave attack. The pebble falls back as the wave slips away. This happens again and again and again. This movement is called Longshore Drift. There's an updrift direction and a downdrift direction, just as there's an upstream and downstream for a river. In places where there's a bend in the coastline, the sediment moving along the coast keeps on going in the downdrift direction. The beach grows out from the shore, forming a feature known as a spit. like Hurst Spit in Hampshire.
The spit is so symmetrical, it looks artificial, in a way, like a road. But of course, it's natural, and it's been here for thousands of years. And it's quite likely that a fair amount of this came all the way from where we started the programme, more than 50 kilometres away at Lulworth Cove, beach sediment.
So far in the programme, we've been looking at coastal processes, assuming that they're taking place in an entirely natural setting. But the truth is, we need one more crucial factor to complete the picture: human intervention. And nowhere is the human factor so blatant as in the area around Bournemouth. 150 years ago, as the country's railway network spread out from the major cities, Bournemouth was one of the scores of towns that sprang up on the coast, adding the human touch to the natural coastline.
Bournemouth is still a major resort today. But it's not just buckets and spades anymore. The look of the beach is important to the town's modern image as an international centre of business, learning and leisure.
This growth in modern business has made the beach an even more valuable asset. The stakes have been raised. David Harlow again.
Could you tell me how important the beach is to Bournemouth?
These 5 miles of golden sands are very important to Bournemouth. In the early days, it brought the passion for sea bathing. The passion for sea bathing brought the paddle steamers, the piers were built. Now we have a party political conferences here. We have thousands of visitors, all sorts of facilities. But in the end, what people really want to see is the beach.
But Bournemouth has always had a problem holding on to its sand, because Longshore Drift has the unfortunate habit of taking it away in vast quantities. To stop Longshore Drift washing away their beach material, Bournemouth started building groins, wooden barriers.
The way a groin works is incredibly simple. It traps beach sediment on its way along the coast on the updrift side. You end up with a strange-shaped beach, but it's better than no beach at all.
To wrestle with nature is an expensive business. A single groin costs around £200,000, but the alternative would be to let the beach disappear and allow Bournemouth's economy to crash, an unthinkable option. A fortune has been spent on protecting the beaches, but in the long term, the sea always wins.
So in the end, by the 1960s, beach levels are extremely low in Bournemouth, and we had to consider beach replenishment. That involved pumping about 1.5 million cubic metres of sand and gravel onto the beaches, and that immediately restored the beaches to their former levels and acted as a very much better coast protection.
To secure the sand, both natural and artificial, there are now 100 groins along the 13-kilometre stretch of the coast around Bournemouth. And no prizes for what comes next. You can't meddle with nature on this scale without a knock-on effect. And there's a clue to what that is right here. Below is the last of the groins to the east, downdrift of Bournemouth. Over the years, it has held back a huge amount of beach sediment that Longshore Drift would have carried farther along the coast to keep beaches going in the next bay. The beaches beyond the groin have thus been starved of material. And look how narrow they are. Let's now go a little bit farther down this part of the coast. It's not that pretty a sight.
Welcome to Barton-on-Sea. They claim this is a seaside resort, but it looks more like a film set for a battlefield. What a mess.
Barton's in a real predicament. Starved of material by the groins in Bournemouth, the town's beach is down to a fraction of its original width. In fact, at high tide, there's no beach at all. Wave energy acts directly on the cliffs.
You may think I'm walking on the cliff top, but no, I'm walking along what used to be the cliff top before it fell down from up there.
Barton's other piece of hard luck is that it's got the wrong rocks in its cliffs. To understand what's happening, we need to take a cross-section through the cliff face. On top is a layer of sandy gravel. Beneath is a layer of clay. The real trouble starts when there's heavy rain. The sandy gravel is permeable, so the water seeps through it. The clay, though, is impermeable and holds water from the sand above and the rain falling directly on it. Soon, the clay turns into a soggy, slippery mass. Then, helped by the waves pounding the foot of the cliff, it happens. This unfortunate phenomenon is called rotational cliff slumping.
It's amazing what you can find on a beach that's had rotational cliff slumping. This is a piece of someone's drain. This looks like a bit of their wall. And up there, a piece of their chimney pot.
Like the rockfall at Beachy Head, the slumping at Barton is one of those coastal processes that has happened extremely quickly. As water gushes from the clay and as the clay oozes out of the cliff face, the shape of the coast can change from one day to the next. The land-sea frontier here is so alive, you have to watch your step every bit of the way. Slumped coastlines are so unstable and dangerous that trying to control them is a really serious business. Any kind of coastal protection requires huge and expensive engineering works. How much to spend and where to spend it often depends on a very simple formula. If the clifftop property is expensive, spend the money. If it's cheap, don't. This is more or less what happened at Barton. Andrew Bradbury, New Forest Borough Council.
Over to the west, we've got a fairly heavily defended stretch of coastline, which has got groins and revetments and cliff drainage works, which has arrested the erosion, protecting the high-value properties. But over to the east here, we've got the soft cliffs, where it would be difficult to introduce an effective coast protection work, and also we've also got relatively low-value property in the form of holiday chalets on the top of the cliffs, and the management strategy adopted there is to simply pick them up and move them backwards when they get within an unsafe distance of the cliff top.
There is a point of view that says that coastal protection is a complete waste of time, that the sea will always win, and that natural forces should be allowed to take their own course. But that view doesn't go down very well in an area like Hampshire, with a huge economy and high property values. The debate about whether to protect the coast or let things go doesn't really get off the ground here.
So what would happen if all this coastal defence work stopped?
Well, obviously the waves are going to carry on moving the sediment with the Longshore Drift immediately. Within 5 to 10 years we'll lose virtually all of the sand on the beach. At that point the groins will start to collapse, and that will expose the seawall to serious wave attack. Given another 5 years or so, most of the promenade would go and the cliffs would start eroding. At that point we're going to start losing another metre per year, so within 200 years you'll lose a swathe of Bournemouth 200 metres deep. As you move towards Hengistbury Head, probably within 50 years we'd have a breach through into Christchurch Harbour, which will isolate the head itself into an island. About 50 years after that you'll have a single bay formed with the head completely gone, just one day.
This is Highcliffe, a seaside town right in the middle of the Bournemouth-Christchurch conurbation, and we're about halfway along the stretch of coast we'll be looking at in this programme. At the moment, the sea's about 500 metres over there, and there's a lot of debate about whether to protect the coastline. But if we don't, all of this could fall into the sea. If that happens, it won't be a question of two, because this spot will be right in it.
The water of the oceans of the world is almost always in motion. Hardly ever interrupted, waves break at the coastlines, sometimes strong, sometimes weaker. There is an enormous energy potential that is available round the clock and free of charge. A potential that, if fully exploited, could satisfy 40% of the worldwide demand for power. This equals the output of 700 to 800 nuclear power stations. Foyt Hydro Wave Gen is developing technologies to convert this inexhaustible energy into electric power without the emission of harmful greenhouse gases. The operating principle of this wave power station is as simple as it is ingenious. An enclosed chamber has an opening beneath sea level, which allows water to flow from the sea to the chamber and back. The water level in the chamber rises and falls with the rhythm of the waves, and air is forced forwards and backwards through the turbine, connected to an upper opening in the chamber. As it is compressed and decompressed, the airflow has sufficient power to drive the Wells turbine. It is a feature of the Wells turbine, named after its inventor, that it is driven in the same direction by both forward and reverse airflow through the turbine. Even relatively low wave motions can generate enough airflow to keep the turbine moving and to generate energy. This is how easily energy can be generated with a wave power station, day and night, all year round, as long as there are waves. The world's first power station of this kind was put in service as early as November 2000 on the Scottish island of Islay and has been feeding power to the grid ever since. Foyt Hydro Wave Gen is convinced of the commercial potential of wave energy. We are certain that our wave power stations can make a significant contribution to supplying the world with climate-friendly energy. Foyt, engineered reliability.